Now let's add some more inference rules to our inventory of axioms. We've already looked at two, modus ponens and simplification. So let's talk now about an axiom called disjunctive syllogism. So disjunctive syllogism is labeled as DS in a proof. And the way disjunctive syllogism works is like this. Let's say we have P or Q, and we have the negation of P, and we can conclude Q. Alternately, we have P or Q, we have the negation of Q, and we can conclude P. Notice in both cases we have a similar operation going on. Let's say we have the square has a well-formed formula, triangle has a well-formed formula. The second premise is the negation of everything in the square. And then that entitles us to conclude everything in the triangle. Similarly, we have a well-formed formula joined to another well-formed formula by OR. We have the negation of the triangle well-formed formula. That's on the right-hand side of the OR. And so we're entitled to conclude everything in the square. So I suggest that you construct a truth table for this, even though because it's an axiom, we know it has to be valid. It'll be good practice. So what you should find when you construct a truth table is that this argument form is not invalid. So we're adopting disjunctive syllogism in the inventory of our axioms. So a quick observation, disjunctive is referring to the fact that it is based on disjunction, and syllogism refers to the fact that we have three statements or expressions. We have two premises and a conclusion. That's sort of the generic way that syllogism is used. It doesn't mean the same kind of syllogism that we saw in Aristotelian logic. Okay, let's look at an example of how disjunctive syllogism looks in a formal proof. So let's say we have an argument, P or Q, and the second premise of the argument is not Q, and the conclusion we want to draw is P. So this is just to review, this is the setup of our formal proof. The argument has two premises and a conclusion, so we set it up just like this with two numbered lines for the two premises we are given, and skip over, use this symbol to indicate the conclusion, and conclude P. So now, given the fact that we have this schema for disjunctive syllogism, it's a fairly straightforward matter of applying that form. So notice we have a well-formed formula in a square joined to a well-formed formula in a triangle by disjunction. That's the first premise of disjunctive syllogism. We have everything in the triangle. That's the right-hand side of the disjunction. Everything in the triangle is negated. That's the second premise. So we're entitled to conclude on line 3, everything in the square, which of course for this argument is P. And our justification is disjunctive syllogism applied to lines 1 and 2. Now, because we've successfully concluded the proof by deriving the conclusion we're aiming for, we will label it QED. And this proof has ended. Okay, great. Let's move on to another inference rule. This is the inference rule conjunction. It's indicated by CONJ. It's abbreviation. Conjunction works like this. Let's say we have a premise P, a premise Q. We're entitled to conclude P and Q. Okay, so let's look at the machinery here. So let's say we have a well-formed formula asserted. We'll put it in a box. Another well-formed formula asserted in the second premise. That's a triangle. So we take everything in the square, everything in the triangle, and join those together by conjunction, hence the name. All right, let's look at how this appears in a formal proof. Let's say on line 1 we have R, on line 2 we have S, and the conclusion we want to derive is R and S. All right, now let's think this through. If you look at the way the argument works, we have a well-formed formula. we can put that in a square. We have another well-formed formula. That'll be in a triangle. And the conclusion is everything in the square and everything in the triangle joined together by disjunction. So that's obviously a case of this schema. I'm sorry, a conjunction. I should have said conjunction. So that's obviously a case of this schema. So what we'll do is we'll write on line 3 R and S, and our justification for that is conjunction, and we've applied conjunction to lines 1 and 2. And because we've derived the conclusion that we were after all along, the argument has successfully concluded. Okay, now let me make a point. Suppose this argument had been on line 1, S, and on line 2, R, and then the conclusion we wanted to derive is R and S. In this case, we can derive the same conclusion, but the difference will be in the order of the line numbers. So here, we will apply the inference rule conjunction to lines 2 and 1. Why is that? Because line 2 has the front end of the conjunction, and line 1 has the back end of the conjunction. So here we have the schema. Here we have these two premises reversed from the schema. And because they're not in the right order, we have to invoke conjunction on the lines, but we have to invoke it in the right order. Okay, great. So now let's turn to one more inference rule for this tutorial. Let's look at addition. So addition is a rule that says that if you have something asserted, you're entitled to conclude that again with a disjunction, and you can add something that you need to it. So let's look at the schema with those geometric shapes. We have a well-formed formula asserted, it's in the square. So we repeat that well-formed formula, use a disjunction, and add something else we need. Okay, great. Let's look at how this appears when we're in a situation of a formal proof. Let's say we have R asserted, and the conclusion we want is R or S. So notice this is a very short proof, but the reason it is because there's only one premise for addition. So obviously what we're going to do is take the element that we're given, it's R, and we're going to conclude R, so that everything in the square, or, and then we need a well-formed formula in the triangle. If you analyze this conclusion, what you see is that what belongs in that triangle for this step in our proof is just S, right? So now we're going to justify that by invoking addition, and we applied it to line 1, and because the conclusion we derived turned out to be exactly what we were looking for, the argument has succeeded. Now I want to take this opportunity to illustrate a point about proofs. So let's think about this. Suppose we have R, and the conclusion that we want to derive is R or S and T. All right, so now what do we do? Well, it's actually not as difficult as it might look, even though this is a more complex expression than just R or S. And here's why. Let's analyze it. The major operator splits this expression into two parts, R on one side and S and T on the other. So if you think about the fact that R is given over here, and you think about the fact that everything in this triangle is just a single thing, it's a well-formed formula that appears in the triangle, just like the schema, then what we end up with is the proof R or S and T. But how do we derive that? Well, we started with OR. That's our square. That's the well-formed formula on the left-hand side of the disjunction. And we added to it everything in the triangle, which is, in this case, S and T. Now, S and T is a well-formed formula, so it can go in the triangle happily. So we've got no problems with the way addition is being applied here, and it allows us to make this argument, to make this proof just like this. We've applied addition to line 1 just like we did here, only what we added to the assertion R is everything in this triangle. So the proof successfully completes.